This is about the population. So again, remember, that means nowhere should any data or any information about the sample be included here. Ever. Okay, so again, remember, I don't know how you're going to get yourself to remember this other than just practicing it over and over. But if you find yourself ever trying to use anything about the sample in your know, that is a surefire red flag that you're doing something wrong.
Yeah.
Wouldn't in any other situation you not even have the
You wouldn't even have the sample. Yes. Absolutely perfect. So sorry, I interrupted you. Say that again.
Well, in any other situation besides doing problems out of the textbook, you wouldn't have your sample before you formed a hypothesis.
I couldn't have said it better myself, right? We never even would have a sample when at this point. Ever. The unfortunate part is that with us, in a learning school class environment, right, we can't possibly go and do studies over and over and collect our own data on every single homework problem we're going to do. So they have to give us some information about the sample. Okay? That might be the single thing that screws most people up, all right? Is we're never going to include any data from the sample. So if it says, and a sample was taken and blah, you should just, hide that part of the question until you've made your known alternative hypothesis. Yes, we won't even have any data to get any statistics from when we're doing this. Okay, so state the null alternative. Okay, and at this level, right, identify the level of significance alpha. All right, this really isn't a step as much as it's. I mean, if you're doing your own study, you're going to have to set alpha and give some justification for it. If you're doing a problem out of the book, you're going to look for whatever, what do they set the alpha value? Okay, so number 3, after we have this, now number 3 is, this is where we go out and collect our data. Okay? Collect our data, or for us, or identify in the problem what the sample statistics are. Okay? Where's the redundancy in that sentence, by the way?
Sample and statistics.
Yeah, the sample statistics. Alright? But let's do it in there again. Just mostly to reiterate, only now are we worried about anything that has to do with the sample. Only now. Okay, so now comes the in-depth part. Okay? Now, number 4. See, it doesn't matter what order you do this in, but we have to find the test statistic.
Wouldn't that be the t-score?
This is the t-score. Yes, this is your z observed or your t observed at this level. And compare it to z star or t star. So if we don't have a z star or a t star, we can't do this step.
Well, if you have a level of significance, you have a T star or a Z star. So.
Well, yes, but you have to go find it. You have to go and find your Z star or your T star. Remember, the T star more than ever. That depends on how big your sample size is.
Yeah.
Right? Every single T star at a 5% alpha is going to be different depending on how many
degrees of freedom.
Yeah, 10 degrees of freedom. Okay, so again, there's 2 things we have to do here. We have to find the test statistic, and we have to find Z star and T star and compare them. And now remember, it's not as easy as just this one's bigger than this one. Okay? In an example here, so example. Direction of extreme to the left, which means this is the direction of extreme, right? So, why is it 0? Why are we in standard normal here?
Because we're trying to find a Z
Our
star
test
and
statistic
it
is
lives
always-
in standard normal.
Yes,
Yeah.
our test statistic is always in standard normal. What is our test statistic? What tells us? What does our test statistic tell us?
It's the amount of standard deviations we need to be extreme.
Yes, you've all kind of got a little bit of it, but at the base level, what is our test statistic telling us?
The number of standard deviations away from the mean.
The number of standard deviations your observation is away from the mean. Yes, absolutely. That is it. That is what the test statistic tells us. The number of standard deviations we are away from the mean. If it's negative, it means we're lower than the mean. If it's positive, it means we're higher than the mean. That is all. All the test statistic is telling us how many standard deviations we are away from the mean based on the null hypothesis. Based on the null hypothesis. That is a test statistic. That'll always be the test statistic no matter what distribution we are in. If we find a test statistic, that's what the test statistic is going to be. Okay, so if this happens to be Z star, then you have to be over here. Then this means this is extreme. And so Z observed has to be less than Z star in order to be extreme. If the direction of extreme is right, same thing, the same concept is happening, right? This is 0, this is standard normal. Now, this might be our T star, okay? And again, I'm just throwing T in there because we use Z over here. The direction of extreme has nothing to do. It's not like only left extremes use Z's, right? Just throwing it in there to give you an idea here. Then this is what it means to be extreme. And our T observed then has to be greater than T star to be extreme. Okay, and notice, Z star and T star, all they are is based on alpha. How many, they're the standard deviation, they're the number of standard deviation that cuts off being extreme or not being extreme. That's what Z star and T star does. Based on our alpha, because that's how we find them, right? Our level of significance. T star and Z star is the number of standard deviations away from the mean you need to be before you're considered extreme. If you're beyond it, you're extreme. If you're not beyond it, you're not extreme.
If you're beyond it, you reject the null. If you're not,
yes,
you don't.
absolutely. Absolutely. So again, right, we can't just, it's not like the p-value in alpha. It's not like the p-value in alpha where if your p-value is not less than or equal to alpha, you are not extreme. Okay? The t, it's a little bit different. Okay, so we're finding our test statistic and we're comparing it to T star and Z star, or Z star, in order to determine if the number of standard deviations away from the mean our observation qualifies us for being extreme based on our level of significance. Okay? Then, again, in no particular order, we're going to go find our p-value. And the p-value is using the null hypothesis. Okay? This is why we tend to find the test statistic first and then use that to find the p-value, because that doesn't depend on any mean or standard deviation because we already standardized it. We needed to use the information from the null hypothesis already to find our test statistic. And so we don't need to use that when we go and find our p-value. If we use the test statistic, the probability of the test statistic, okay? But we don't have to. But again, the p-value, we're going to find the p-value and compare to alpha. Okay, so we found. So in order to do this, I guess an unspoken thing here then is we need to, I guess 3, 4a or whatnot, you need to come up with your approximately normal distribution, right? For our null hypothesis, we need to come up with our approximately normal distribution. And if you're in a mu, it's going to be mu and sigma over the square, or either sigma over the square root of n, or it could be mu and what? What if we don't have a sigma? Well, no, we're in mean still. Right, we need the standard error, right? Our S, our standard error from our sample, is going to be S over the square root of n. Yeah. And if we are in proportions, then it's going to be normally distributed as P and the square root of PQ over N. Okay. Any questions? I wish I could put that somewhere else, but whatever. Is there any questions with that? Okay, if we don't know these, we're toast. We don't know these, we're toast. Okay? Notice it's never, ever, ever been just sigma. Not when we're doing hypothesis tests. Okay? More people lost more points on the take-home because almost nobody, there's a couple people, only a couple people divided sigma by square root of n. That should just be immediate. If you don't have n somewhere in your samples here, or in your standard deviations, why? Do you guys remember why we have to deal with the square root, with the sample size?
Because of the other equation that it comes from is.
Well, so you're thinking too hard. Right? You're trying to involve too much equation stuff here. Remember, we are doing all of this. All of this is possible because this is a distribution of sample means or sample proportions. So we took if we took every possible sample of size n, all of those samples would either have a p hat or an x bar, depending on what we were looking at. Okay? Every possible sample of size n. They'd either have a bunch of p hats or we'd have a bunch of x bars. All of those will form a normal distribution centered around the true population proportion or the true population mean. Okay? And so the reason we have to include our sample is because the bigger your sample, the closer you are to your population and the more accurate you are, the less deviation there is. Okay? And that's where this n comes in. That's why it came in over here, because, we're going to have a different standard deviation based on a sample distribution from samples of 4 as we are based on a distribution of samples of 30, which is going to be different from samples of 500. You see what I mean? we're not just now taking, we don't know the population anymore. We can't just say it's sigma. Okay, what we're saying is, look at this, it's going to be centered around here, but the standard deviation that we think it is going to be different based on how big our sample size is.
And also, at that point, it's squared before it comes into that equation. So just
Well, this was squared. Yes,
yeah, that's
here,
what I mean. So that's, and so is S.
Right, and so basically what we did is we had the variance and we took the average variance. Right? Remember, each one of those samples had a variance. And so we just took the average. If we took every possible sample of size n,
Yeah.
right? All those samples would have a variance. The average of all those would be the true population variance. And so when we come in and take the square root, it was sigma squared over n, right? And when we take the square root, it
Just
sigma
sigma.
squared, square root of sigma squared is sigma.
Yeah.
Square root of n is n, square root of n. Okay, that's where this came from.
Mm-hmm.
Okay, all of this is possible because we're assuming that we took every sample of size n and we built a distribution, and that distribution is centered around the true population parameter that we're looking at, whether it's p proportion or whether it's a mean. Okay, and so if we don't have n somewhere in our standard deviation, that again is a red flag that we made a mistake. All right, so if you just naturally start going through something and you set up your approximate normal distribution, if you don't have n worked in somewhere in there, that's a sign that we're going down the wrong direction. Okay? So, this is the deal. And now, we're always going to use the p-value compared to alpha, and the p-value is from, right? We've always found the p-value assuming that the null hypothesis is a distribution that's true. Because again, what we're saying here is if we really did take samples of size, every single possible sample of size n, and build a distribution of a bunch of p-hats or a bunch of x-bars, then if this is a true population mean, and that should be the center of our distribution. And so, what are the probability of me grabbing data and being that far off if this really was a distribution? That's what we're testing. Okay. And then, of course, at the end, we write it up in sentences again. You write up results based on, right, you're based on number 4. And we can also, one thing that we will do, okay, and so write up the results. I should mention one thing. There's another wrinkle here, okay? If h bar is not equal to, which means, or h bar, if h not, if our alternative hypothesis is not equal to, right? What does that tell us?
Two-sided.
Two-sided, right? If two-sided, include confidence interval in the hypothesis test. And remember, if it's two-sided, including the confidence interval in the hypothesis test means we're going to build in the confidence interval, and if the null hypothesis mean is in that confidence interval, then we don't reject. If it's not in there, then we reject. But it's got to be two-sided if we're going to include that. If it's not two-sided,
So if it's not in the confidence level, we don't reject?
no. If that, remember, the confidence interval is we're saying that,
The mean is
yeah, that we're confident that the mean is in that interval. So if we build a confidence interval and the null hypothesis mean is not in that confidence interval, then that's telling us that we don't believe that's the true population mean. Because if it was the true population mean, it should be in there. Or we just got a bad sample. That's possible. I mean, that's type 1 error right there. But it is what it is. So if it's not two-sided, we still build the confidence interval and offer it in number 5. We don't use it as the actual part of the test, but we're still going to build it and offer it, right? We're going to use p-value and their test statistic to make our decision, but later on we're going to say we're rejecting the null. Oh, and here, by the way, here's a 95% confidence interval that we think contains the true population mean. Okay? We're not going to mention anywhere that we're using this confidence interval to reject or not reject the null.
And that's
Only if it's two-sided do we do that.
why. Because it,
Why? Because the way in which we have to build a confidence interval is two-sided. We can't build a confidence interval one-sided, right? Because remember, that t-star, we're adding on and subtracting off from that value, and that's two-sided.
okay, so,
That's the only kicker there. All right? If it's two-sided, then we're going to use the confidence interval in our hypothesis test. That's going to be a third piece of information that we say reject the null.
But don't we still make confidence?
Oh, yes.
We still
Yes.
make them, but they're just not a deciding factor.
Yes, so that's right here. If not two-sided, we build a confidence interval and offer it in number 5. It's not part of our actual decision. We're going to say we reject the null because the p-value in our test statistic compared to our star statistic is what you call it. But we think this is when we got 95% confidence that this interval contains a true population parameter. Okay, is there any questions? Okay, so on Thursday, or today's Thursday, on Tuesday I handed you out some practice problems. Okay? What I want you to do is go back over some of those practice problems. I got them circled here. I think you should look at 36, 38, 39, and 41. I want you to do these by hand. No calculators, no one prop Z test, no T test. You need to do these by hand. Do the hypothesis by hand. Meaning you've got to go and physically find you're going to be building this distribution. You're going to be finding your test statistic by hand. You're going to be finding Z star and T star. Obviously, that's not by hand. That's an inverse normal. But when I mean by hand, I mean if you need to use normal CDF, you're using normal CDF. If you need to use inverse normal, you're using inverse normal. If you're going to have to go through and write down the formula for your test statistic and do it out by hand in your calculator, then you're going to have to go and find Z star and T star. Then you're going to have to go and find the p-value by hand. And again, by hand means inverse normal, or not inverse normal, but normal CDF with either your test statistic or you can use your actual value. Okay, because people, I've seen it. You need practice on this. And again, I don't feel comfortable letting you go to one prop C tests and T tests
I just wrote out
without knowing how to do this by hand and knowing what these mean. And of course, the more you spend writing up, the more you're going to understand what it means, because in the write-up, you're going to force yourself to say something like, look, our observed test statistic means that we were this many standard deviations away from the mean. But what it means to be significant was this many standard deviations away from the mean from our T star. Our observed value was more standard deviations away from the cutoff value of T star. Therefore, we have to be extreme. That kind of thing. That's what we mean. That's why I'm trying to have you write these things out in such detail, because it's not just so I can watch you write sentences out. It's so you can describe what it is that your statistics mean. Okay, so go ahead, get into groups and work these out. Does anybody not have it? You need some? Okay, so 1, 2. Does anybody else need one of these?
All right, I'll stop that for now.
So